Hello, everybody. This is going to be our post-lab discussion for the enthalpy of combustion lab. That's what I called it. If you remember in this lab, we went ahead and first off, we burned some alcohol, collected the heat from that alcohol on a calorimeter. And by calorimeter, I mean a soda can filled with water surrounded by foil. And then we used that same setup to gather the heat from some burning potato chips and try to figure out the number of calories in those chips by collecting the energy they gave off. So if you're struggling on that lab or you just want to make sure that you got everything right, here we'll kind of do an overview of the whole purpose of the lab, and then we'll talk through some of the questions a little bit for you to help fill this little guy out. All right, so let's go ahead and switch screens for a second. All right, what do we got here? Okay, so in a lot of the normal stoichiometry problems we've got a balanced reaction, and it tells you the enthalpy change for this balanced reaction. In this case, if I combined 2 moles of sodium hydroxide with 1 mole of something called hydrogen sulfide or hydrosulfuric acid, I would release 39 kilojoules of heat. That's what that negative sign indicates. So, maybe if I was solving a stoichiometry problem like this, I would say, maybe I have 5.00 grams of this that I drop into just a big old beaker of hydrosulfuric acid. So there's extra stuff there. And so the math that I would do here, if I want to predict how much heat is going to be released by this reaction, I just have to go through and 5.00 grams, turn grams into moles. I know that there are 40.00 grams in 1 mole of sodium hydroxide. That's what the periodic table tells me when I calculate the molar mass. And then based on this balanced reaction, for every 2 moles of sodium hydroxide we would release 39 kilojoules of heat. And that would give off let's see, I think with significant figures, it's 2.44 kilojoules of heat. So this balanced reaction is for molar amounts, 2 moles and 1 mole, but we typically don't have an exact mole of something. And so we have less, or we just have a certain number of grams, because that's what we can weigh out on our balances. So instead of 2 moles, if I just have 5 grams, this is the heat that I'd release, and I can calculate that using the enthalpy change that typically we can just look up, or that's given to us in a chemical reaction. But that's not what we did in our lab this time. This time in our lab, we wanted to figure out what that enthalpy change was. And the way we did it is that we did the chemical reaction. We measured the amounts of everything we had. We did the chemical reaction and we collected the heat, and we figured out how much heat was released. And then we could work backwards and determine that enthalpy change. So how did we find out how much heat was released? Well, first off, I guess before that, you burned a certain amount of alcohol. So we're looking at question 1 in the first 4 parts on the back. You burned a certain amount of an alcohol called ethanol. And you lit it, you let it go for, 30 seconds, maybe 60 seconds. And let's pretend that you produced a mass of 0.60 grams. Well, not produced a mass. You weighed it before and after you did the combustion, and this was a difference in mass. So we know we had that much ethanol in excess oxygen, and we're trying to use that to get to the enthalpy change. So we've got 0.60 grams of C2H5OH. That's what we're going to start with. We're going to do the same stoichiometry problem, except now we're missing that number, but I'll show you how we'll get it. So again, this is my number, the 0.60 grams. You've got a different number based on your data. I'm going to look up the molar mass. If I remember right, it's like 46 point blah, blah, blah grams. I don't know. You can calculate how much 2 carbons, 6 hydrogens, and 1 oxygen weighs. We have that many grams in 1 mole of ethanol. And then according to this balanced reaction, there's only 1 here. When I combust 1 mole of ethanol, I release, the big number we're looking for, some number of kilojoules of heat. I don't know how many. That's what we're going to solve for. And whatever that number is, that's our answer to this problem. But the thing is, we can only solve an equation like this if we have, if there's only one variable. We know how much heat was released by this reaction, though, because you've got an exciting little equation that looks like this. Q equals mc delta T. So in just a second, I'm going to show you where we got the mass of the water. This is the specific heat capacity of the water, 4.18, and the change in temperature. You measured how much heat was released, so you can plug these numbers in, solve for that, and then plug that number up here after you divide by 1,000 to turn it into kilojoules. And then you'll have a number over here, and then you can solve for x, because 0.6 times 1 times x divided by 46 point blah, blah, blah equals, well, whatever that is. Make sure over here, though, you make that negative. Even though when you plug the stuff into Q equals mc delta T, and it's going to be positive, well, you were measuring the heat going into the water. So that's an endothermic reaction. So that was a positive enthalpy change. But you know from burning that alcohol, I don't know if you put your hand over it or touched it, but it was hot. Heat was being released. So you'll get a number here, but make it negative when it's up there. All right, let's take a look at our lab data sheet for a second and see where some of these numbers come from. And at least this will give you a good start. Oh, slow school computer. Just a second, I'll share screens for you so you can see what we're talking about. Ah, there we go. All right, here we go. All right, so at this point, you've got this entire little guy filled out. So what do we have on here? Well, first off, we're going to need to be able to do Q equals mc delta T. And so we can get that by using these numbers. You know how much the calorimeter weighed at the beginning, that empty soda can, and then you added water. So you can just do a little subtraction of these two numbers, and that's going to give you your mass of water in grams. Mass of alcohol burner before and after combustion. So right now for that whole question 1, we are just looking at this little column here, the ethanol trials. Chips come later. All right, we can go through the mass of the alcohol burner before and after. And that's going to give us grams of our alcohol, in this case C2H5OH. In my example just a second ago, this is where I got the like 0.60 grams. I just made up a number there, but yours should be less than a gram. It should be a pretty small amount. And then here, and we've got our starting temperature and the highest temperature we reach during combustion. We can subtract there and get a delta T, get a change in temperature. So that's all the stuff we need. Remember, C we can just find on our formula sheet. C is a constant and Q equals mc delta T, and it's 4.18. So you've got all the stuff right here you need to be able to do the math that I just did over there. So go ahead and do it. Here, as we look at these problems over here, we've got enthalpy change of water and enthalpy change of alcohol. So you get to use Q equals mc delta T a couple different times to solve for enthalpy change. Just see if you can, they're going to be the same number, but see if you can figure out which one of those would be positive and which one of those would be negative. Because it's the same amount of heat both ways. We're just pretending that all of the heat went directly from that combustion of ethanol right into the water. It's just that one was exothermic and one was endothermic. One has a positive enthalpy and one has a negative. Here is where you're going to use your little stoichiometry guy and solve for x. Putting Q over here, remember it's negative, and we can go ahead and divide it by 1,000, so it's in kilojoules. So here's your stoichiometry. And what you're going to get here for part B is you're going to be getting the measured value of the enthalpy change, or experimental, however you want to look at it. In this problem, though, I give you the actual value, or the accepted value for the combustion. You plug that in here, and we can solve for percent air. Now I would expect a pretty big percent error on this. If you remember, our calorimeter was just a soda can with water surrounded by foil. That's probably going to give you a percent error somewhere in the like 60s or 70s. It wouldn't surprise me at all. Pretty big. A lot of people, a lot of the labs that have been turned in so far were giving me numbers, you know, your enthalpy change was somewhere around like -300, -400, and that's pretty good. All right, and I think based on what I've talked about here, you can probably think through that little guy. All right, jumping down to number 2. Same type of thing here. We've got enthalpy change. So you're going to be using Q equals MC delta T. Nothing too wild. You know where those numbers come from. Grams of chip combusted. Well, for each of those 2 chip trials, and those trials, the data wasn't great for those, which is why we did it twice, and we'll just average the results. Because 2 results averaged is pretty much always better than 1. So you can go ahead and look at the difference in mass before and after you burn the chip. That's going to give you your grams of chip that's combusted that you will use here for 2B. Once you have an answer to 2A, an enthalpy change. So you have joules. Down here you have grams. Then you take joules divided by grams to get your, well, your amount of energy per unit of mass. How is that useful to us? Well, once you have joules per gram, then you can go here and you can compare it to the food label. So the nutritional label on these chips said that there's 150 food calories per 28 gram serving. So 150, I'll just say FC for food calories in 28 grams. Man, I'm great at writing with a mouse. All right, so you've got a couple steps in stoichiometry to see if you can use these conversions and convert, well, grams are fine, but you need to go to joules per gram. So can you convert food calories into joules? And you have joules per gram, multiply everything on top divided by on bottom, and then you can use that value, which is what we would think of as the accepted value. You can use that, compare it to what you determined here, which is your measured value, and we can find percent error that way. So the amount of energy in that chip that the nutritional label says, which we assume is right, versus the amount that you say, which we're pretty sure is wrong because you lost a ton of heat. And then we can see percent error there. So it'll let us practice some of the math that we've been doing so far. All right, hopefully that helped you out a little bit. Best of luck. And if you have questions, either ask me in class or shoot me an email. Have a good one. Talk to you later. Bye.